So coordinate 3 was um, Fourier transform. In Fourier transform, first we established that we have two views. We have time view and frequency view. That's what we can easily see as human, and that's why we have to decompose. Then we said there are two views, time and frequency views, and we said that we can go back and forth in these views with respect to Fourier transform and Fourier transform inverse. Then comes a formula, and I made you understand that where the Fourier transform formula comes. So that was, you would take the wave, wind it around the circle, and so with various winding frequencies, right? So it depends which frequency you want to wind with. And then you draw the center mass. Center mass, when I say center mass, that means the amplitude of the center mass. You draw, and what you represent in this drawing is the x and y coordinates. And that's where the formula for Fourier transform as minus infinity to infinity, if you are doing Fourier transform of this, e minus 2 pi j t dt comes out to be. Okay, and then we understood this, that coordinate system, which is based on the Euler formula, that tells us if we have a point and we draw a circle, oops, not a good circle, so I can reach this point different routes. I can reach this point through, oh, I have not changed it, excuse me. So I can reach this point through this route, or I can reach this point through this route. Right? So, and this point will be consisting of, then I gave you the formulas for then I gave you formula for various formula related to Euler's formula, where you can combine cosine or sine in terms of Euler's formula. And that was the background of Fourier transform. Then we talked about the where we use Fourier transform. Then I told you that the big uses in network communications are modulation. And whenever we write modulation, convolution comes because we multiply two functions, f of t, gt, in um, time domain, and we sort of do convolution of these functions in frequency domain. So that's why when I say modulation, convolution is already sort of there embedded. That was, so whenever we do modulation, we, and they also are one of the applications of Fourier transform. And the other thing which is very common, which is again a sort of modulation, but we know it as sampling. And we cannot convert any analog data into digital data without sampling. So, and what we do actually in both of them, we multiply two functions in time domain, and that is happening as a convolution. So once we said this, then there were 4 or 5 numericals. My whole answer was that we don't concentrate much on the mathematics because that's not the purpose, but we do simple mathematics. So there were a number of different problems. I solved the problem of related to cosine omega t. Then I gave you, I said you can try sine omega t in the notes. There were, so these are all the time domains, except that I gave you sort of that you can do of a box, or you can do a straight line, there was another question that you have, this one. So these were different type of questions to practice and understand Fourier transform. And let me mention, in all these, we have been trying to go to time to frequency domain. This week, I will post some questions where you will go from frequency domain to time domain, and that by meaning you are talking about Fourier transform inverse. So what you will be doing, you will be multiplying with e j omega t, right? Not minus, minus will become plus, and then you will be integrating with respect to dw, if it's in w or f. So I will post 1 or 2 questions on this. So that was a little practice on understanding the formula and how it's applied. The key thing in many was how you tackle the integration of this function. How you tackle the integration of this function, and you know the formula is wrong, and there was a slide which mentioned all these formulas. Then when we move to the 4th quadrant, and in the same quadrant we talked about, the properties, Fourier properties. And there was a mention of that Fourier pairs are some well-known pairs. Example, a cosine is having 2 deltas, direct deltas, or box is having a sink, so that people don't need to do the mathematics, and right away they would know, but you need to have a practice what your x and y coordinates would be. And then we looked at different properties. I discussed duality. So duality means if I have This is in time domain. Its Fourier transform, and the frequency domain will be a sink. And if I bring a sink here in time domain and I do its Fourier transform would be a box square. So that was duality. We talked about scaling, and I gave you the example of the expansion of um, I draw one box and I expanded it, and I showed you the impact of scaling on both um, the impact of this on the y-axis amplitude, it would be affected, and the zero crossings of the frequency domain equivalent would be impacted, where the zero crossings are happening in the frequency domain. If I change the size of the box and I draw you, I told you how it would impact. That's in time domain. So changes in here, changes in time. So that's where the scale happens. Changes in time will impact the amplitude and the frequency. How? I showed you. Then we talked about the yeah. Then I guess somebody's messaging, so I'm not looking at the screen yet. So let me finish, and then I can see if you have something. So yeah. So then we talked about other. So that was scaling. 1, 2, 3. Then we talked about the time shifting. And we talked about frequency shifting. And I took you to that simulator and I showed you what would be the impact in time shifting. I summarized that what we are actually doing, we are changing the phase. And here I summarized that you are bringing in the notion of e j omega t in time axis. And we observe that we are getting like real and imaginary components in time axis. But I told you we will be more practically involved in the applications like modulation. Yeah, properties. So these are properties, I'm saying application, modulation and convolution. And from here, we entered into the fourth course.